All right, so here we go. So here's that stuff that I handed back that I've graded. I've still got a good bit of grading to do, so I'll keep working on it here. So here we go. So this first one here, you've got a cantilever support. So the thing again, common things that might cause problems with these free body diagrams. One is over-analysis. Okay, I see a fixed support, I do that. I'm done. Okay, I don't think a bit more about it. I see a smooth surface, I want a force that's perpendicular to the surface. There's the load, we've got a wind force over here, and we've got a cable force there. I did the trigonometry and found the angle. So that's the first one. Do we have any questions on that? Okay, good. All right. Okay. Now, next thing here is the, now the other thing I'll point out about this has come up, and it came up a little bit in the homework. In physics, I know you do things with objects. You consider them, you analyze them like they're particles, okay? We don't do a whole lot of particles in here in this class, so I don't want any dots for free body diagrams. That just doesn't work for us because the dimensions on the objects matter, okay? And it's come up a couple of times, so I just want to mention it again, okay? So, and you kind of have to compartmentalize, and I know it's difficult because you might be doing Math 254 and physics in this class, and I know they get a little jumbled because we approach things differently and all that. It's just something I don't really quite know the answer. I mean, mathematicians and physicists and engineers all look at things differently, and it's kind of, and you see that reflected in how we teach stuff. So you kind of have to compartmentalize what you're doing to the class you're working on. Okay. Okay. Now this one here, I got the weight. I've got a pin joint. When I see a pin joint, I just do that. Two perpendicular forces. Then I've got a ramp. Now the force is perpendicular to the ramp. The ramp makes a 20-degree angle, so that means if I take 90 minus 20, I get 70. That's the angle of the force. That's what I want. Okay. Good with that one? Questions? Okay, now this one might be the trickiest of the bunch. What you have to do is identify what the flat surface is. The other thing we're doing here is we're showing the forces on the glass plate. We are not showing what the glass plate does to the surfaces. We are showing what the surfaces do to the glass plate. And what they do is they exert forces. Okay, so these surfaces exert forces. The commonality in these forces is because it's smooth. They are perpendicular to the flat surface. So you have to identify what the flat surface is. At A and this might be lettered differently than what you had. So I'm not sure. That's a little bit of an old copy there. Why don't we see what we can do about that? So yeah, we got A over here now. So that's A. Here's B. We've got C up here, and then we've got D. So it's slightly renumbered. There we go. So we've got RA here, we've got RB there. So at A and B, the flat surface is the surface itself, the corner there that's holding up the glass plate. At D, the surface is the wall. But at C, with that round connection and the glass plate is the surface because it's a flat surface leaned up against that round connection. So when you take 90 minus the 67, what you get is 23 right there. So are we okay with that? We got any questions on that one? All right, the next one there, we got 6 points of contact on that when you have that stack of pipes. Okay, you can count them. They're evenly spaced. So if you take 360 degrees and divide it by 6, you get 60 degrees. So there's 6 forces, 60 degrees apart. You also have the weight. Okay, the last one there, we've got the motor exerting a couple or a moment, whatever you want to call it. We got a pin joint holding up the motor. We've got the roller. And then there would also be the weight. Okay. So that's the deal on those free body diagrams. You know, we do want to draw those properly and with the proper angles on the forces. So if you don't draw them with the proper angles on the forces and properly, you can't get the right answer when you work through the problems. Okay. So we good with that? Do we got any questions? All right. So in that vein, let's have a look at this one here. This is the next one down the line in these examples we've been going through. So we've done kind of the basics on this trigonometrically based equilibrium. Let's have a look at a few kind of special cases, you might say. So this is a little different number than what that shows. This is now 440. So let's say I've got this bar up at an angle like that at 20 degrees. All right, so what I'm going to do here is I'm going to look at G, 1.2 meters from A on the bar. I would assume that's running parallel to the axis of the bar, so that would be something like that, 1.2 meters. Okay, that's G. And that would be where the weight of the bar is applied, and that's 240 newtons. Okay. Now for the rest of this free body diagram, I'm just going to have a look there at the forces applied. I mean, I've got the weight of that bar. I see that pin joint at A. And when I see that pin joint at A, I realize the thing's going to try and rotate about A. All right. I have this cable at B. Now cables pull, so I have that force right there. You might call that the tension at B. For some reason they use T a lot with cables. You could call it RB. You could call it FB, whatever you want. And then we're going to have the force at the pin joint, all right? So that'd be how you'd look at that. Now this approach on this one, I'm going to have these forces, and the way we've been doing these so far, getting that one, especially at B, is going to get a little bit tricky when you look at that, because I think what we would have to do to get that would be to get two dimensions and then break the force up into components. So I would take that force and break it up into X and Y components, and then I would combine those forces with dimensions. So I would need to get this dimension for the X force, and then I would need to get this dimension for the Y component of force. And that's how I would have to work through that, all right? And that would get a little bit, you know, it's certainly doable. It's not that horrible or bad or anything, but it would be a bit of work. There might be a better way to do this, and there is a better way to do this. All right? So let's look at a better way of doing this problem. An easier way. What I'm noticing here is I've got a triangle there. What do you suppose this angle is right here on the triangle? What is that angle?
42 and 48, and subtract out 180.
Okay, yes, yeah, there's a lot of ways to do that. Although I don't know if this is 42 here. 42 is with the horizontal. So yeah, we got to be a little careful there. How about a simpler way? We've got 20 degrees here on this line, on a horizontal. So what does that leave left over for the angle with the vertical? You're just overdoing it. What do we got there? Somebody? Okay. Now somebody just give me something, okay? Seriously, just guess. 70, there we go, thank you. That's 70, okay. There we go, okay. That's a 90. I'm going to take 90 minus 20. That's 70, okay. All right, so now I can figure out that third angle, can I? Now we're going to do that 180 thing, right? Because we know a triangle is 180. We're going to take away 70. We're going to take 48. And it's 118 from 180. Is that 62 in there maybe? I think. Okay, great. So there we go. So we got a triangle like that. All right, now, once we've got that, we can now start to work with this a bit, because now what I know is that that angle right there is 62 degrees. That's something that I want. Also, what I've got are the dimensions along the angled armature. I've got 1.2, I'm given that. I'm given the full length of the armature is 3. So that's going to get me a situation like that, 1.2 meters and 1.8 meters. All right, so sometimes when you have these kinds of problems, the best way to approach them is to use an angled coordinate system. And that's legal to do that. All right, so I can go ahead and do that. So rather than do it in this fashion, which will get, it's not horrible or anything, but all the same, it gets a little complicated. I could do it an easier way. What I can do is use an inclined set of axes. I can go with axes like that. Okay. Now the difficulty in this, the thing that makes it a little bit trickier, is I got to figure out some angles. Like I had to find that 62-degree angle right there. But other than that, it's fairly straightforward. Okay, I need to find that 62, which I just found. I also need to realize that that's 70. And the way I realize that is I've got a 20-degree angle here. And then that vertical force there is coming straight down. And then I've got 70 there, okay? All right, now one thing I noticed, at least when I was working out here, is, some of the things I learned in school meant more than others. And one thing that I used a fair amount when I was working was geometry skills, okay? And the one thing about geometry is draw a picture and prove it to yourself. I don't know if they still do geometry in the way they used to. They used to make you do all these proofs, all the time, which, it has a use here. Be sure you're sure on this stuff. Draw a picture, put the numbers in, and check it out. Okay, I'm quite confident that's 70 degrees now that I've drawn that picture. Okay, so it's helpful to do. All right, so now I can go ahead and do that to figure this thing out. What I want to do, I want to find the reaction at the pin joint and the tension in the cable. Now, notice what I've done with RA and RAY and X. I've inclined them so that they'll line up with my axes, okay? And that's fine to do that as long as RAX prime and RAY prime are at right angles. I can go ahead and do that. They do have to be at right angles, though, for me to do much with them, okay? So once I've got that, off I go. So how about taking, how would you start this problem? What's the standard drill on this stuff, on these problems? Yeah, we're going to take moments about where are we taking? Yeah, about A, okay? Because two unknowns act there. You can solve for the third. So why don't you take a moment about A and get that tension. Now use this inclined axis system. I gave you a moment problem. It was a while back, of course, but I did that for homework, if you remember, where I had you turn it on an angle. It's a good trick. That's why I did that. So why don't you find that cable tension, okay? Let's see if you can get that. And see, this moment equation is a lot simpler if you can draw that sketch that I've got. It just becomes a lot easier. It involves a lot more components and things if you don't do that. If you do it this way, it's quick. It's quicker and I think easier. So it's a good trick to know. So maybe just take a couple minutes and get that started. Moment about A. Let me know if you got questions. some moments about A is 0. You've got that 240 Newton force. And then you got the tension at B. So there's only 2 terms in this. See, that's why I like to do this. I get a simpler moment equation out of it. Now you're going to have some trig on both terms. So there might actually be 3 parentheses on account of the trig. Y'all get into that? I mean, what do we got going on there? Yeah, I want to get that 240 newtons, right? And what I want is, I want a component like that. That's what's going to cause the moment about A. I want that to be perpendicular. So to get that, I want what? Opposite the 70-degree angle. What I'm doing is taking that component and just kind of shifting it over, so to speak. So what's my trig on that? Sine 70. Okay. And then I've got that moment arm it was given. It's 1.2 meters. Okay. So that's how I approach that. I look at the component of force, and then I put in the moment arm. Then I look at it, and I go, well, if I'm looking at that thing, if that's a wrench, and I push on it like that, it's going to come around clockwise. Clockwise is negative, so I put a little negative sign out in front of that. I don't put the signs in the parentheses. I put it outside after I look at it. Okay. So that's negative sine 70, 240 times 1.2 meters. And then I can do a similar thing with that tension at B. It's just I don't know the force. I don't know the magnitude. But I know what I call it. It's TB. Okay. And then what do I got? I got 1.2 and 1.8. So I got 3 meters. And then that gets me this bit right here, right? So I need the opposite side from the angle. So that'll be sine of 62. And that's going to come around that way. That's positive because it's counterclockwise. So I got a negative on the first term, positive on the second.
And the cosine of the Newton going down doesn't do anything because it goes straight towards the RA.
Yeah, right. I'm not bothering with the cosines because they have a 0 moment arm. Both of them do, right? Yep. So that's the deal, okay? Because they go right through A. So I don't have to bother with them. Okay? So I could go ahead and run that, and I will get 102 newtons for TB. So we doing all right with that? We got any questions? Okay. Now, so now I've got that. Now, once I've got that, I can just do force equations to solve for the other two, all right? Okay. So some of fx and some of fy will get me rex and ray. Now, I'm doing them at an angle there, okay? So, you know, I have to remember that. So I'm putting a prime on there just to indicate that I'm finding not the standard rex and ray, but I'm finding them at angles. Now, if I want to know the total force in RA, I could take the square root of sum of the squares, and I could get 188 newtons. You might think of that as being the total force in the pin that goes through the pin joint, though it's a little trickier than that. It kind of depends on how the pin connection is configured, but that's kind of the idea there, all right? So we okay with that? So just a little trick there. Sometimes if you've got something on an incline, if it's at an angle, just reorient your axes. Okay? Now you can always use the original method I showed you. It's just sometimes it's a little bit more work. You know, you could have done this one with a standard XY coordinate system too. You would have had to do a little bit of calculations there to find moment arms. That would have involved trig. And it would have got just a little bit more complicated, that's all. Okay. So are we good with that? We got any questions on that? All right. And then notice that that total pin force is 188. Okay. All right, now let's look. Now, I don't know if you need to copy all this down, but let's have a look. Had I used standard XY coordinates, all right? Now, had I done that, I would have had to do the trigonometry to get those moment arms, X and Y, to get to that tension at B, all right? Like that. And it would have been a more involved moment equation. Now, I would have got the same answer. I mean, the tension in B is what the tension in B is. I mean, you know, it would have come out to 102, just like before. But it would have been more involved because I would have had X and Y components for the moment arms. You can see what I'm doing there. I'm breaking that up into X and Y components, okay? Now, the other thing with this is once I do that, if I were then to solve for REX and REY, I would have got different answers for REX and Y. I would have got 76 and 172. Okay, because I'm using different axes. On the example that we just did, we were using axes like this, and the X and Y's were based on those axes. Now I'm using standard axes. So I'm getting different answers. But look what happens when I take the square root of some of the squares. I get the same answer. The total force is what it is. How the components are just depends on what orientation you're looking at. Okay? So you want to kind of understand that little difference there. So that's one trick to get through an inclined problem is like that. Questions on that? Okay. So that's one thing you might run into. Now, another thing you might run into is 442. Okay. Now, 442, we have unknowns, but they're based on distributed load reactions. So if you build a dam or something like that, the soil will push back up in a distributed load. Quite often when you're doing a dam, the assumption is, the basic assumption you make is you've got a pin here at what they call the cutoff wall, and that the water force then starts to push on the dam, and it will rotate the dam like that, and the soil will then push back. And the soil will push back in a pattern, kind of depending on how hard that rotation causes the base of the dam to push against it. So the further out from the pin, from that assumed pin joint at that cutoff wall you go, the greater the soil reaction. Now, you know, again, I've talked about this a number of times. Now, you could have a look at that. Yeah, it may not be an exactly perfect model, but it's the one we use. Okay, it works pretty well. Okay, so that's the assumption there that you can make. So let's look at an assumption like that. Let's kind of look at this problem here, and let's try and solve for a distributed load. So I'm on 442. So let's say I've got a person in a boat, and I've got the weight of the boat is 2,400 newtons, and the weight of the person is 900 newtons. The person in the motor are in the back. Okay, let's figure out what these water reactions are on the boat. So I've got those forces in their proper location. I don't know if I called that point out A or not, but I've got it marked here. On the far left, we'll call that A. And what I've got then is I've got 2,400 newtons at the center of gravity for the boat, which is in the middle. Then I've got 900 newtons at the very end of the boat, which is the combined weight of the person and the motor. And I want to figure out what these values are on this distributed load. What's that value and what's that value? Okay. Okay. All right, now here's how I could go about doing it. What I'm going to do, I'm going to do equilibrium, you see, because I don't know either of those forces. There's kind of, well, you might say two unknowns. I'm going to go ahead, so two unknowns, I'm going to generate two equations to solve it, okay? So with equilibrium, what I got sum of fx is 0. But see, that one's not going to do me much good because I don't have any x applied forces. This is all about y forces, so that one ain't going to help. But I can go sum of fy equals 0, and then I can take sum of moments about a equal to 0, okay? And those two equations that I could use to find those two values. I just have to get a little bit systematic about how I approach that distributed load. All right. So let's see. What we're going to do is find the reaction on that equals the rectangular load, and then I've got a triangular load over it. So what I'm going to do is kind of chop this across like that with a straight line, and I'm going to turn this into something I can handle, which would be a rectangle and a triangle. I'm going to call this P1 over here, and I think I'm going to call that P2 over there. Okay. So that's what I'm going to do with this. And then I'm just going to treat those as they're unknowns, but I'm just going to carry them through the equation here. So for the rectangle, the base of the boat is 2.4 times the distributed load of P1. And that'll be 1.2 meters from A. That's where that centroid is for the rectangle. It's half of 2.4. So that's getting me 2.4 P1 at 1.2 meters from A. That's what that is. Now the other one, what's happening here is I have this load pattern like this. It's going to kind of rock back a little bit at the back of the boat, you know, because of the weight of the motor and the person back there. What I'm going to do, of course, I'm going to chop this straight across. So this is P1 on either side. So the area of that rectangle is 2.4 times P1. Well, this is P2, which is the total distance. So this becomes P2 minus P1. That's the height of that triangular load. So that's what I'm doing for that second run. I'm going 1/2 times the base of 2.4 times the height of the triangle, the difference between P2 and P1. And that's what I'm doing. So when I run through that calculations, I take half of 2.4, which is 1.2 times P2 minus 1.2 times P1. And that will be at the centroid of the triangle, which is this distance right here. 2/3 of 2.4 is 1.6. Half of 2.4 is 1.2, okay? So that's where I'm getting those distances. So now what I can do, see, I can just call those forces, and then I can find the moment that they cause. Whoops, I got them going the wrong way, don't I? Whoops. We're doing that because that's the water force pushing up. Then I can balance those with the weight of the boat and the weight of the person, which are the things coming down. So I'm going to come up with a moment equation. I have those forces. They're not numbers yet, but they're expressed in terms of variables. Okay. So for sum of Fy, I got the two forces down, the 2400 and the 900 down, so they're negatives. And then I've got the two water reaction forces up. So that's 2.4 P1 plus 1.2 P2 minus 1.2 P1. So I'm getting the sum of forces is 0. It's negative 2400 minus 900 plus 2.4 P1 plus 1.2 P2 minus 1.2 P1. All right, then I just kind of go through the process there of getting that resolved. So I'm going to combine the 2400 and the 900, so that's negative 3300. And that's going to be 1.2 P1, which is 2.4 P1 minus 1.2 P1 plus 1.2 P2. So I can solve that for P1. I'm setting up a substitution here, so P1 is 2750 minus P2. Okay. So that's one equation that has P1 and P2 in it. So we all right with that? Now that's a force equation. I can also generate a moment equation. So I'm going to take those forces and multiply them by the moment arm. So I'm going to take a moment about A and set that equal to 0. Okay. So sum of MA is 0, and that's going to equal, and I'm just going to put these different terms in here now. So what do I have? I've got 2400 newtons, and that's 1.2 meters from A, and it looks to me like that's going to come around clockwise, right? So that'll get a negative. And then I've got 900 newtons. And 1.2 and 1.2, that makes 2.4 meters. And once again, that's going to come around clockwise, so that's going to get a negative. Okay. Then I've got this stuff pushing back. Now the stuff pushing back here is the water, and I've got those two water loads, and I've got all that information up above. And again, that's why I like to do it that sort of thing, because it's all lined out there for me. I've got 2.4 P1, 1.2 meters away. Okay, that's going to come counterclockwise, right, like that, so that'll get a positive. The other one's counterclockwise too, and that's a little bit more involved. And so I've got 1.2 P2 minus 1.2 P1, and that moment arm is 1.6 meters, like so. Okay. I know if you're here, that might be a little hard to read this. I'm coming to realize this room doesn't work so well for these slides, but so here we go. Minus 2,400 newtons times 1.2 meters. Minus 900 newtons times 2.4 meters. That's the weights. The weight of the boat and the weight of the person. Plus 2.4 P1 times 1.2 meters. Plus this load of the triangular distributed diagram, or this triangular piece down here. The distributed load, which is 1.2 P2 minus 1.2 P1 times 1.6 meters. Now that's a little bit, I don't know what the word is. They used to say gnarly or whatever. It's got a few pieces to it. So you'll notice what I'm doing here is I just kind of walk down it nice and simple, okay, step at a time. So the first thing I did was multiply everything together. Then I realized I've got, let's see, what do I got here? I'm going to take the numbers, which are these, and I take them to the other side of the equation, and they become positive. I collect terms on the letters, so that's what's happening there. Then I'm going to divide through by 0.96, and so my goal here is to get an expression for P1. I get it down to there. Then I've got two expressions for P1, so I set them equal. Solve for P2, back solve in, and solve for P1. That's what I'm going to do. So step-by-step solution there. I don't like to rush that, all right? So that's getting me the two values there on that distributed load. So what I've got on this side, I have 2,500 newtons per meter. On the other side, I've got the sum of the two, so that'll be 2,750 newtons per meter. So there's the distributed loads. 2,500 on the left, 2,750 on the right. Okay, like so. All right, so we all right with that? Same process, just a little bit more complex inputs. Yeah, question?
What do we have for the first P1? We got 2750 minus P2. But then up there you have...
So right up here, that's the first one that you're calling out? I'm doing a substitution. Yeah. Good? Okay. All right. And this math gets a little complicated, so that's why I'm doing it that fashion. If you have a problem like that in homework, if you've got a solver and you want to use it, go ahead and use it. That's fine. All right. So there's a couple a little bit more complex type of problems. So we good with that? Okay. All right, let me take a break here then, if we're good. For a few minutes. Start up at about 5 till. Okay.